Welcome, everyone. Get ready because today we're jumping right into the ultimate diagnostic masterclass explainer for the AWS Certified AI Practitioner exam. We're going to test your readiness against 10 real-world scenarios covering the absolute fundamentals of artificial intelligence in machine learning. We've got a whole lot of ground to cover, and I'm going to challenge you to lock in your answers as we go. So are you ready to see where you stand? Let's do this. Okay, let's dive right into this. Round 1. Taxonomies and classification tasks. Here's your very first scenario. Imagine a junior developer is trying to understand the relationship between different subfields of modern artificial intelligence. They ask you how to technically categorize a massive neural network model like GPT-4 compared to your traditional classification models. The question is, which statement represents the most accurate nested hierarchy of machine intelligence? Take a look at the options. Is it A, B, C, or D? I'll give you just a second to lock in your mental choice. If you went with C, you absolutely nailed it. Notice how the concentric circles map this whole thing out. Artificial intelligence is the broadest category. It's the grand umbrella. Inside that is machine learning, which uses data-driven discovery. Drilling down even further, we hit deep learning, which leverages multi-layered neural networks. And sitting right there in the very center, we have generative AI. This is exactly where models like GPT-4 live, driving the massive content generation boom we're seeing today.
Let's keep this momentum going. Scenario 2. A data scientist has developed a machine learning model to forecast continuous housing prices in US West 2 based on regional characteristics. They need to evaluate the accuracy and variance of the model's predictions. The question? Which combination of mathematical metrics should they implement? Read through A, B, C, and D. And hey, pay really close attention to the word continuous here. Go ahead and lock it in.
The correct answer is C. You know, whenever you see the word continuous on the exam, consider that your absolute cheat code for regression metrics. While classification handles discrete categories with metrics like precision and F1, continuous regression evaluates using things like mean absolute error, root mean squared error, and R-squared. Moving right along to our third scenario. Let's say an automated content moderation system scans media assets and flags each asset with one or more categories: violence, adult content, or profanity. A single media asset can actually have multiple categories simultaneously. For example, it could be tagged with both violence and profanity at the exact same time. So how should this machine learning task be classified? Is it binary, multi-class, multi-label, or linear regression? What's your gut telling you? The answer is C, multi-label classification. And this brilliantly illustrates a really critical difference. Binary is strictly one of two options, spam or not spam. Multi-class means choosing exactly one category from many, like identifying a dog, a cat, or a bird. But because our moderation categories are non-mutually exclusive, meaning an asset can be violent and profane simultaneously, it is specifically a multi-label task. Excellent work so far. Now we're shifting gears into round 2, understanding learning paradigms. This round is going to challenge you to shift your mindset toward how different systems actually learn from data out there in the real world. Scenario 4 reads, a financial services firm wants to build an automated risk containment pipeline that flags potentially fraudulent credit card transactions. The transaction data is highly unstructured, lacks target historical labels, and fraudulent cases represent rare outliers in the network. Which learning paradigm and algorithm implementation should the architecture team select? Review the options carefully. The sheer lack of labels is a massive hint for you here. If you guessed B, you are spot on. Let's trace the logic on this flowchart together. First off, do historical labels exist? No. That immediately rules out supervised learning like QnA, routing us strictly to unsupervised learning. Next, what's our goal? To find rare outliers. Therefore, an anomaly detection model, specifically an isolation forest, is the perfect architectural choice because it isolates those rare anomalies without needing any pre-labeled examples. Next up, we have a massive language model scenario. An engineering team is pre-training a large language model, and they want to understand the underlying mechanics of self-supervised learning. The question? How do self-supervised models learn syntactic and semantic representations of raw text without human annotation? Take a moment to read through the 4 options. How does a machine actually learn without a human holding its hand? The answer is B. So the crucial point here is that self-supervised learning totally eliminates manual annotation through pretext tasks. The system takes raw text, autonomously masks a token, and forces the prediction node to guess the hidden word. By doing this millions of times, the model generates its very own pseudo-labels, saving human engineers literally thousands of hours of manual tagging. Scenario 6 takes us into the industrial space. Picture this. An industrial facility wants to train a robotic system to optimize HVAC power draw while maintaining a target temperature. The system learns through a continuous loop of executing actions, observing the physical state of the building, and receiving mathematical feedback. How are the components of this reinforcement learning loop technically classified? Look really closely at options A through D. Which one correctly maps the agent, the environment, and the actions?
The right answer is C. Reinforcement learning is all about a continuous feedback loop. The agent is our decision maker. That's the robotic control software. It interacts with the external environment, which is the physical building, by executing actions like adjusting the temperature. The agent then receives a reward, allowing it to autonomously learn the most efficient policy over time.
All right, you've made it to the final gauntlet. Round 3, model mechanics and algorithms. Let's finish strong. Scenario 7. During validation, a machine learning engineer notices something pretty alarming. A neural network model achieves 99% accuracy on the training dataset, but drops all the way down to 64% accuracy on the unseen test dataset. How should this model fit be classified, and what technical steps should be taken to mitigate this issue? Notice that massive performance drop from 99% down to 64%? Lock in your answer.
Answer D is the one. This is literally a textbook case of overfitting, or high variance. Notice how the blue training error drops to near zero, meaning the model is perfectly memorizing training noise. But that orange test error starts spiking up. It's completely failing to generalize to the real world. Mitigations for this include regularization, early stopping, or data augmentation.
Scenario 8 is a classic data engineering challenge. A data engineering team is working with a large dataset containing over 250 input features. They want to compress the dataset's feature space by reducing the number of variables while preserving as much statistical information and variance as possible. Which built-in unsupervised SageMaker algorithm should they select? Is it DeepR, PCA, K-means, or XGBoost?
The answer is B, principal component analysis. Now, what's really interesting about this slide is seeing how that high-dimensional 3D data is projected down onto a flat, lower-dimensional 2D grid. PCA does exactly this mathematically. It discards redundant features while preserving maximum variance, making it the ultimate tool for compressing a massive feature space.
Almost there. Scenario 9. A retail chain wants to build a demand forecasting model for thousands of seasonal items across multiple regional distribution hubs. The demand patterns depend heavily on sequential historical sales, price fluctuations, and regional weather. Which specialized SageMaker algorithm is optimized for this type of time series forecasting? Think about sequence and time here. Is it SVM, PCA, DeepAR, or GAN?
The correct choice is C, DeepR. DeepR is basically AWS's heavyweight champion for complex forecasting. It doesn't just look at a single line of data. It leverages recurrent neural networks to ingest multiple related time series, like sales history, weather, and price changes all at the exact same time, generating a highly accurate probabilistic forecast.
Here it is, the final scenario of the masterclass. A generative AI engineering team has trained a base large language model but notes it occasionally outputs helpful but toxic instructions regarding hazardous compounds. They want to implement reinforcement learning from human feedback, or RLHF, to fix it. What is the correct order of phases to implement RLHF? Look closely at the exact sequential pipeline required to align this model. Lock in your final choice.
If you picked B, you finished with a perfect score. Let's move to the next breakdown and see how this builds across the 3-step pipeline. Step 1 is supervised fine-tuning, which trains the base model on safe demonstrations. Step 2 requires humans to rank outputs to train a mathematical grader, known as the reward model. Finally, Step 3 uses proximal policy optimization to update parameters and actively penalize that toxic behavior.
And that brings us to the ultimate Domain 1 synthesis, the fundamentals blueprint. Everything we covered today, the generative AI hierarchy, classification types, learning paradigms, and core mechanics, is summarized right here. This is your master cheat sheet. Take a screenshot, study it, and internalize it. After surviving these 10 complex scenarios, I leave you with one final question. Are you ready to crush Domain 1? Thanks for joining me on this explainer.